In this lesson, we are going to talk about binary tree traversal. When we are working with trees, we may often want to visit all the nodes in the tree. Now, tree is not a linear data structure like array or linked list. In a linear data structure, there would be a logical start and a logical end. So we can start with a pointer at one of the ends and keep moving it towards the other end. For a linear data structure like linked list, for each node or element, we would have only one next element. But tree is not a linear data structure. I have drawn a binary tree here. Data type is character this time. I filled in these characters in the nodes. Now for a tree, at any time, if we are pointing to a particular node, then we can have more than one possible directions. We can have more than one possible next nodes. In this binary tree, for example, if we will start with a pointer at root node, then we have two possible directions. From F, we can either go left to D or we can go right to J. And of course, if we will go in one direction, then we will somehow have to come back and go into the other direction later. So tree traversal is not so straightforward, and what we are going to discuss in this lesson is algorithms for tree traversal. Tree traversal can formally be defined as the process of visiting each node in the tree exactly once in some order. And by visiting a node, we mean reading or processing data in the node. For us in this lesson, visit will mean printing the data in the node. Based on the order in which nodes are visited, tree traversal algorithms can broadly be classified into two categories. We can either go breadth first or we can go depth first. Breadth first traversal and depth first traversal are general techniques to traverse or search a graph. Graph is a data structure, and we have not talked about graph so far in this series. We will discuss graph in later lessons. For now, just know that tree is only a special kind of graph. And in this lesson, we are going to discuss breadth first and depth first traversal in context of trees. In a tree, in breadth first approach, we would visit all the nodes at same depth or level before visiting the nodes at next level. In this binary tree that I'm showing here, this node with value f, which is the root node, is at level 0. I'm writing L0 here for level 0. Depth of a node is defined as number of edges in path from root to that node. A root node would have depth 0. These two nodes D and J are at depth 1. So we can say that these nodes are at level 1. Now these four nodes are at level 2. These three nodes are at level 3. And finally this node with value H is at level 4. So what we can do in breadth first approach is that we can start at level 0. We would have only one node at level 0, the root node. So we can visit the root node. I'll write the value in the node as I'm visiting it. Now level 0 is done. Now I can go to level 1 and visit the nodes from left to right. So after F, we would visit D and then we would visit J. And now we are done with level 1. So we can go to level 2. We will go like B, then E, then G, and then K. And now we can go to level 3, A, C, and I, and finally I can go to level 4. This kind of breadth first traversal in case of trees is called level order traversal. And we will discuss how we can do this programmatically in some time. But this is the order in which we would visit the nodes. We would go level by level from left to right. In breadth first approach, for any node, we visit all its children before visiting any of its grandchildren. In this tree, first we are visiting F, and then we are visiting D, and then we are not going to any child of D like B or E along the depth. Next we are going to J. But in depth first approach, if we would go to a child, we would complete the whole subtree of the child before going to the next child. In this example tree here, from F, the root node, if we are going left to D, then we should visit all the nodes in this left subtree. That is, we should finish this left subtree in its complete depth. Or in other words, we should finish all the grandchildren of F along this path before going to right child of F, J. And once again, when we will go to J, we will visit all the grandchildren along this path. So basically, we will visit the complete right subtree. In depth first approach, the relative order of visiting the left subtree, the right subtree, and the root node can be different. For example, we can first visit the right subtree and then the root and then the left subtree. Or we can do something like we can first visit the root and then the left subtree and then the right subtree. So the relative order can be different, but the core idea in depth first strategy is that visiting a child is visiting the complete subtree in that path. And remember, visiting a node is reading, processing, or printing the data in that node based on the relative order of left subtree, right subtree, and the root. There are three popular depth first strategies. One way is that we can first visit the root node, then the left subtree, and then the right subtree. Left and right subtrees will be visited recursively in same manner. Such a traversal is called pre-order traversal. Another way is that we can first visit the left subtree, then the root, and then the right subtree. Such a traversal is called in-order traversal. And if root is visited after left and right subtrees, then such a traversal is called post-order traversal. In total, there are 6 possible permutations for left, right, and root, but conventionally, a left subtree is always visited before the right subtree. So these are the 3 strategies that we use. Only the position of root is changing here. If it's before left and right, then it's pre-order. If it's in between, it's in order. And if it's after left and right subtrees, then it's post-order. There is an easy way to remember these 3 depth first algorithms. If we can denote visiting a node or reading the data in that node with letter D, going to the left subtree as L and going to the right subtree as R. So if we can say D for data, L for left, and R for right, then in pre-order for each node we will go DLR. First we will read the data in that node, then we will go left, and once the left subtree is done we will go right. In order traversal, first we will finish the left subtree, then we will read the data in current node, and then we will go right. In post order, for each node first we will go left, once left subtree is done we will go right, and then we will read the data in current node. So pre-order is data left right, in order is left data right, and post order is left right and then data. Pre-order, in order, and post order are really easy and intuitive to implement using recursion, but we will discuss implementation later. Let's now see what will be the pre-order, in order, and post order traversal for this tree that I've drawn here. Let's first see what will be the pre-order traversal for this binary tree. We need to start at root node, and for each node we first need to read the data, or in other words visit that node. In fact, instead of DLR we could have said VLR here, V for visit. We can use any of these assumptions, V for visit or D for data. I will go with DLR here. So let's start at the root. For each node we first need to read the data. I'm writing F here, the data that I just read. And now I need to go left and finish the complete left subtree. And once all the nodes in the left subtree are visited, then only I can go to the right subtree. The problem here is actually getting reduced in a self-similar or recursive manner. Now we need to focus on this left subtree. Now we are at D, root of this left subtree of F. Once again, for this node we will first read the data, and now we can go left. We will go towards E only when these 3 nodes A, B, and C will be done. Now we are focusing on this subtree comprising of these 3 nodes. Now we are at B, we can read the data, and now we can go left to A. There is nothing in left of A, so we can say that for A, left subtree is done, and there is nothing in right as well, so we can say right is also done. Now for B, left subtree is done, so we can go right to C, and left and right of C are null. And now for D, left subtree is done, so we can go right. Once again for E, left and right are null. And now at this stage for F, complete left subtree is visited, so we can go right. Now we need to go left of J, and there is nothing in left of G, so we can go right. And now we can go left of I. For H there is nothing in left and right. Now at this stage left subtree of I is done and right subtree is null. And now we can go back to J. The left subtree for J is done, so we can go to its right subtree. Finally we have K here, and we are done with all the nodes. This is how we can perform a pre-order traversal manually. Actual implementation would be a simple recursion, and we will discuss it later. Let's now see what will be the in-order traversal for this binary tree. In in-order traversal, we will first finish visiting the left subtree, then visit the current node, and then go right. Once again, we will start at the root and we will first go left. Now we will first finish this subtree. Once again for D, we will first go left to B, and from B we will go to A. Now for A, there is nothing left, so we can say that for this guy, left subtree is done. So we can read the data, and now we can go to its right, but there is nothing in right as well, so this guy is done. Now for B, left subtree is done, so we can read the data, and now for B we can go right. For C, once again there is nothing left, so we can read the data, and there is nothing in right as well. Now left of D is completely done, so we can visit it, read the data here. Now we can go to its right to E. For E, once again left and right are null. At this stage, left subtree of F is done, so we can read on the data, and now we can go to right of F. If we will go on like this, this finally will be my in-order traversal. This tree that I'm showing here is actually a binary search tree. For each node, the value of nodes in left is lesser and the value of nodes in right is greater. So if we are printing in this order, left subtree and then the current node and then the right subtree, then we would get a sorted list. In-order traversal of a binary search tree would give you a sorted list. Okay, now you should be able to figure out the post-order traversal. This is what we will get for post-order traversal. I leave it for you to see whether this is correct or not. I'll stop here now. In next lesson we will discuss implementation of these tree traversal algorithms. Thanks for watching.